Hello everyone. So we'll be looking into the structure elucidation of PGE1 with the stereochemistry. So we have already seen that prostaglandins are cyclopentane containing ring groups with long side chains, and also they have got double bonds. But these long chains, their stereochemistry is that they are trans with respect to each other. That means at position number 8 and position number 12, when I look at the carbon atoms, they both are trans with respect to each other. Where this speaks about the stereochemistry. So the stereochemistry is something like this. The OH groups are alpha, that means they are below the plane. The long chain systems are trans with respect to each other. So also we can see that there is a carbonyl carbon at position number 9, that means it is an E series. If there is an OH at position number 9, it is an F series. In E series, there is a carbonyl carbon at 9th position, there is an OH at 11th position and an OH at 15th position respectively. This system is also speaking that the OH are alpha with respect to each other. So this is what is your PGE1. When we speak about PGF, it means that there is an OH at position number 9, both of which are alpha with respect to each other. Many of the prostaglandins have got cis double bonds. Let us look into the example of PGF2 alpha. There is a double bond between 1, 2, 3, 4, 5 and 6. This is cis with respect to the long chain system which is at position number 8. Why we also speak it to be a cis system is because OH at 9th position, 11th position and 15th position along with this long chain system at the 8th position, all of them are below the plane and hence they are said to be a system where we can see that they are cis with respect to each other. When we look at the second long chain system and the first long chain system, both of them are trans with respect to each other. Hence, this is what is called as the stereochemistry in prostaglandins. Naturally, these prostaglandins, they can be synthesized by the biosynthesis. So, it means the biosynthesis could be followed by a 20 carbon atom containing acid or a long chain fatty acid called as arachidonic acid. Now this has got 20 carbon atom like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 and 20. As we have seen that there is a prerequisite for the prostaglandin. Prostaglandins should have 20 carbon atoms. So the starting material is taken as arachidonic acid. This arachidonic acid upon oxidation cyclizes to give a cyclopentane system along with the addition of oxygen across the double bond. And at the 15th position, there is an introduction of perhydroxy system. This particular system upon reduction will give us PGF2 alpha. That means carboxylic group at position number 1, OH at position number 9, 11 and 15, double bond between C13 and C14, a double bond between C5 and C6. Double bond between C5 and C6 is cis with respect to the OH and both the long chain systems are trans with respect to each other. This is how the biosynthesis of the prostaglandin takes place. But in organic chemistry, we see that the synthesis has to be done in the laboratory. Before we actually design any synthesis, we have to go through the various reagents, various types of reaction that are required in the synthesis. So reactions and reagents used in the synthesis of PGF2 alpha. We'll be doing PGF2 alpha. Further, we shall be ending it with PGE1 system. So the scientist who actually did this particular synthesis was E.J. Corey in the year 1969. This was published in the paper JACS, that is Journal of American Chemical Society, in the year 1969 with the volume number 91 and page number 5675 respectively. So he started with the synthesis of PGF2 alpha. So the starting materials that he proposed was cyclopentadiene system, chloromethoxymethane, 2-chloroacrylonitrile, copper 2 tetrafluoroporate. So these are some of the starting material that have been proposed. The first named reaction in this particular synthesis would be a Diels-Alder reaction. When a diene and a dienophile reacts with each other, they give a Diels-Alder adduct. This Diels-Alder adduct can act as an intermediate for various types of reactions. So cyclopentadiene, when it reacts with chloromethoxymethane, we get a methoxylation. This shall give me a diene system and a dienophile, which is further utilized in the synthesis of an Diels-Alder adduct. This is one part of the reaction. Further moving on, the next reagent is metachloroperbenzoic acid. This reagent is used in a Baeyer-Villiger oxidation. In Baeyer-Villiger oxidation, from a ketone, either an ester is synthesized, or if the ketone is cyclic in nature, then a lactone is synthesized. This is done by the help of peroxides like metachloroperbenzoic acid. Further, the next reaction is usage of Ki3, that is potassium triiodide, in the reaction called as iodolactonization. This is a system where an iodine and an oxygen will be acting across a double bond so that we get a lactone. Like for example, there is a presence of a double bond in this particular structure. When we add a Ki3, there is an addition of oxygen and iodine across this particular double bond. This system is called as iodolactonization. In general, the iodolactonization can also be spoken as your halolactonization. Why halo? Is because instead of iodine, there can be other halogen which can be added upon. But generally, because iodine is a very good leaving group, hence iodolactonization is being utilized. The next reagent in this particular system is tributyl tin hydride. Tributyl tin hydride helps in the hydride producer system. That means it produces a hydride system, which is actually helped by a radical initiator called as Isobutyl. That means a butyl system is present and a nitrile system is present. This particular reagent is called as AIBN, Isobutyl, which is a radical initiator. BBr3, that is boron tribromide, is also used so that there is an addition reaction. CrO3.2Pr, that is, it is called as chromium 6 oxide with pyridine, commonly called as Collins reagent, is the next reagent in this particular reaction. This is utilized in Sarrett oxidation. This is conversion of a primary and secondary alcohols with the help of Collins reagent to yield aldehydes. Aldehydes are again a proper intermediates for an introduction of a long chain system. The next reagent is dimethyl dimethyl 2-oxo-heptyl phosphonate. That is, this is a long chain which is utilized so that onto my cyclopentane ring there is first long chain can be utilized. That is at the end where we end up with the methyl system. So this is utilized with a solvent called as dimethoxyethane. This reagent is utilized in a named reaction called as Horner-Wadsworth-Emmons reaction. Dimethyl 2-oxo-heptyl phosphonate is a stabilized carbanion system. This stabilized carbanion system across which is present in the Sarrett oxidation, that is an aldehyde which is generated at a Sarrett oxidation system, there is a carbonyl carbon because there is a generation of an aldehydic system. So dimethyl 2-oxo-heptyl phosphonate would react with an aldehyde or ketone which are said to be phosphonate carbanion system. They will predominantly yield an E-alkene, because whatever we are looking in the final synthesis is I should get two trans-related long chain system. So Horner-Wadsworth-Emmons reaction speaks that when a stabilized phosphonate carbanion react with aldehydes or ketones, they should produce predominantly E-alkenes. Zinc borohydride is the next reagent which is a strong reducing agent. 3,5-dihydropyran system is helped for the protection for an OH group. The next reagent is Diisobutyl aluminium hydride, again which is a reducing agent. The reagent is triphenyl phosphonium ylide. This triphenyl phosphonium ylide is utilized in a Wittig reaction. Wittig reaction is nothing but ketone reacts with a phosphonium ylide to give me an alkene. The other reagent in this particular Wittig reaction is Dimethyl sodium, that is sodium methyl sulfonyl methylide. This aids up for the Wittig reaction so that we get an alkene. To get an alkene system, there are two reactions that we are utilizing. One is Horner-Wadsworth-Emmons reaction and the second one is Wittig reaction. So the various named reactions that are utilized in this particular reaction systems are Diels-Alder reaction, where a diene plus a dienophile gives a Diels-Alder adduct. Baeyer-Villiger oxidation, where ketone gives an ester or a cyclic ketone will give a lactone. Iodolactonization, across the double bond there is an addition of iodine and oxygen respectively. A Sarrett oxidation, where primary or secondary alcohols will give us aldehydes. Horner-Wadsworth-Emmons reaction, where stabilized phosphonate carbanions react with aldehydes or ketones to give E-alkenes. And finally, Wittig reaction, where ketone and triphenyl phosphonium ylide will give an alkene. So these are the few named reactions which are utilized in the synthesis of PGF2 alpha.